All right, this is pre-AP, pre-calculus, notes 10.4, double angle identities. In this lesson, we're going to derive identities for sine of 2 theta, cosine of 2 theta, and tangent of 2 theta using the sum identities that we learned in the previous section. So let's review. Well, let's introduce this new thing, and then that's going to force us to review. Sine of 2 times theta, I think we could all agree, is the same as sine of theta plus sine of theta. Now that's a double angle identity for sine, which is sine of the first angle times cosine of the first angle plus sine of the second angle times, I said that wrong. This is the first angle, second angle, and then sine of the second angle times cosine of the first angle. Well, look, we got these two terms are identical, which means we have two of those. Hey, what, my thetas are just terrible lately, ever since the war. So this is the double angle identity for sine, which you need to memorize. Double angle identity for cosine. So we got cosine of 2 theta. That's going to equal, this is me showing you where the identity is coming from right now. It's equal to cosine of theta plus theta. Well, that's equal to cosine of theta, first angle, times cosine of the second angle, minus sine of the first angle times sine of the second angle. Well, cosine of theta times cosine of theta is cosine squared of theta. Sine of theta times sine of theta is sine squared of theta. So this is a double angle identity for cosine. Now this can be manipulated to produce two more identities, which you can choose to use or choose not to use. For example, if we replace the left side of, if we replace cosine squared of theta with a Pythagorean identity, that would get replaced with 1 minus sine squared of theta. Or it could be replaced with it, doesn't have to be. So then that reduces to 1 minus 2 sine squared of theta. That is also equal to cosine of 2 theta. So these two identities are derived from each other. So you could think of it as two different identities, or you could just think of it as one. Similarly, we could replace the sine squared here, if we wanted, with 1 minus cosine squared of theta. If you distribute the minuses there, that's going to end up giving us cosine squared of theta minus 1 plus cosine squared of theta, which gives us 2 cosine squared of theta minus 1. So there's three identities for the double angle identity for cosine. To be honest with you, I pretty much exclusively use this one here. Moving on. Double angle identity for tangent. Let's think about what tangent of 2 theta would be equal to. Well, that's going to be equal to tangent of theta plus tangent of theta. That's the sum identity for tangent, which is tangent of the first angle plus tangent of the second angle over the difference of 1 and tangent of the first angle times tangent of the second angle. Well, that's going to give us, in the numerator, 2 tangents of the angle divided by 1 minus tangent squared of the angle. So this is the double angle identity for tangent. Needs memorized. This right here, to be clear, is a minus. Number one, suppose sine of theta is negative 3 over 2, negative 3 over 5, and the tangent of theta is greater than 1, greater than 0. I'm having a hard time reading. And I'm going to sneeze again. Answer the following questions about theta. In which quadrant does theta terminate? In other words, where's the terminal side? Explain your reasoning. Well, we know that sine of theta is y over r, which means y is -3 and r is 5. So from this, we can say that sine of theta must be in quadrant 3 or 4, because sine is negative. Since tangent of theta is less than 0, and that means that the sines of y and x are opposites, which means our terminal side. Now, when is x and y different signs? Quadrant 2 and quadrant 4. Well, if you combine these two ideas, it's got to be in 3 or 4, and then it's got to be in 2 or 4. Well, then it must mean oops, I'm sorry, I said this wrong. Since tangent of theta is bigger than 0, the signs have to be the same. Can you say same? Which means the terminal side, the signs of x and y are the same in quadrants 1 and 3. So that must mean that the terminal side must be in quadrant 3. Thus, theta terminates in quadrant 3. Easier way to sum that up, because I messed that up at the beginning and that probably caused confusion. We can see from this that y is negative and r is positive. Since tangent is greater than 0, that means both sine and cosine have to be negative, or they both have to be positive. Since we already know y is negative, that means x has to also be negative. This only happens in quadrant 3. B, draw angle theta and label the reference triangle. Well, we established this in quadrant 3. This is always going to be a right reference triangle. We said from what we were given that y is -3 and that r is 5. This is a Pythagorean triple, 3, 4, 5 triangle. Quadrant 3, x has to be negative. Once again, we know this because sine of theta is -3/5. 6, order sine of 2 theta, cosine of 2 theta, tangent of 2 theta from least to greatest. That should be pretty easy. Sine of 2 theta, according to the double angle identity, is 2 sine of theta times cosine of theta. Well, sine of theta would be y over r, which looking back at our picture, that's -3/5. Cosine is -4/5. This ends up being 5 times 5 on the bottom, and on the top, -3 times -4 is -12 times 2 is 24. Keep in mind, the directions are supposed to order things, so we haven't ordered anything yet. Cosine of 2 theta is the double angle identity, cosine squared of theta minus sine squared of theta. That's one version of it. Cosine of theta is -4/5. Supposed to square that. Minus sine squared of theta. Sine of theta is -3/5. I'm supposed to square that. So that's going to be 16/25 minus 9/25. That makes this 7/25. Cool? Then we got to do tangent of 2 theta. tangent of 2 theta is equal to 2 times tangent of theta divided by 1 minus tangent squared of theta. Tangent of theta is y over x, that's negative 3 over 4, which reduces, negative 3 over negative 4, which reduces to 3/4. On the bottom, we have 1 minus 3/4 squared. 2 times 3/4, you can do some cross canceling, and we get 3/2. Our denominator, 3/4 squared is going to be 9/16. I'm going to change the 1 to 6/16 so I can subtract those. Run out of space quickly. That's going to give us 3/2 divided by 7/16. Dividing by a fraction is like multiplying by its reciprocal. So this is going to be equal to 3/2 times 16/7. Nothing, yeah, we can reduce a little bit. We can divide both 2 and 16 by 2. It's going to give us 24/7. Hopefully you're a little bit smaller than me. We didn't answer the question yet. Order sine of these double angles from least to greatest. So cosine of 2 theta is the smallest. Sine of 2 theta is the middlest. And tangent of 2 theta is the largest. Cool. Hey, we're almost done. Verify that each of the following is an identity. I'm going to start with the left, and I'm going to change cotangent and tangent into terms of sine. That's going to be sine and cosine. It's going to be cosine over sine for cotangent and sine over cosine for tangent. Common denominators, I'm going to multiply this first fraction by 1 in the form of sine over sine. I'm going to multiply the second one, I'm sorry, not by sine over sine. I'm going to multiply the one on the right by sine over sine. Multiply the one on the left by cosine over cosine. Gives me common denominators. So when I put those together, I'm going to get cosine squared of theta minus sine squared of theta over sine of theta, cosine of theta. Now cosine squared of theta minus sine squared of theta, that's cosine of 2 theta over sine of theta, cosine of theta. It's interesting. Now I don't know what else to do with the left, to be honest with you. Kind of stuck. So I'm going to work with the right now. The right is 2 times cotangent of theta, cotangent of 2 theta. Cotangent of 2 theta is the reciprocal of tangent of theta. Well, let's do this. Let's make this cosine of 2 theta over sine of 2 theta. That's a good idea. Cosine of 2 theta, I'm just going to leave because I already have that on the top on the left. I'm going to change the denominator, sine of 2 theta, into its double angle identity, which is 2 sine of theta, cosine of theta. Choose cancel. Now the left and the right are the same. I think my microphone is dying, or maybe already died. Just going to check the battery real quick. Left and right are the same, so that's good. Oh, I'm okay. I'm at 7%. I can certainly finish this with 7%. Number 3, verify this is an identity. I work with the most complicated side, which is the left. I have double angle identities on the top and bottom. I'm going to change sine of 2x into 2 sine of x, cosine of x. I'm going to change cosine of 2x into cosine squared of x minus sine squared of x. If I simplify the left, the bottom, I'm going to get 1 minus cosine squared of x plus sine squared of x. I recognize that this right here is the same as sine squared. Sine squared plus sine squared is going to be 2 sine squared. Then I can cancel a 2 from the top and the bottom and a sine from the top and the bottom, which leaves me with cosine of x over sine of x, and that reduces to cotangent of x, which is what the right side was all along. How about that? Last one. This one looks interesting. Right side's obviously more complicated, so I'm going to start with it. I'm going to GCF a sine of x and a cosine out of these terms. It's going to leave me with cosine squared of x minus sine squared of x. Well, I recognize what this is. That is the double angle identity for cosine. And I don't know what else I could do with the right. So let me start with the left now. This is the same as sine of 2x plus 2x. So it's a double angle identity for sine. That, each of these, okay, so that double angle identity for sine, we're going to have 2 times sine of 2x times cosine of 2x. Make sense? And then I can change, so let's see what we have the same. We have this the same on each side, so I don't want to mess with those. But somehow this, let me change the color, this becomes this. So I'm just going to bring the cosine of 2x down. Let's use this double angle identity again. So sine of 2x is going to be 2 sine of x cosine of x. And then we have it. 2 times 2 is 4. Sine of x cosine of x times cosine of 2x. That's what the right side was for quite some time. It's proven, so it is finished. Awesome.